I don't want to spend too much time on this. I actually don't want to ask any questions on the T about this because if you learn this, you will learn it in a numerical analysis class. That's where they spend a lot of time worrying about errors. But what kind of errors can we expect for numerically solving this thing? I just put T0 to be 0 because you can shift it if you want to. There's truncation error. Versus round off error. We know from Euler's method that Euler's method is kind of crap because it's and it actually doesn't do bad on kind of nice curves that you should already see that, like the one I just did for the y prime equals y minus t squared plus 1. It looked almost identical to the Runge-Kutta method, so it did pretty well there. But we know from the Euler's method, what we call truncation error, that the error is proportional. So this is truncation. Truncation means just cut it off. I always get these wrong. I think it's big O, that your error is proportional to. That means when you have big O of h squared, then your error is proportional to h squared. Written out, it means that truncation error is equal to a constant times h squared.
Is this always true or just for Euler's?
It's only true for Euler's, right? And just to remind you where that comes from is taking this and expanding it around if this is the Taylor series for this y, I'm assuming it has one. And then if I just chopped it off on the first two, this is Euler's method. So this part here is Euler's method. And this stuff right here is a truncation. I just cut off the Taylor series and just took the first two terms. So that's what Euler's method does. And y prime is just f, the right-hand side. And I just made it autonomous so that you can see the math. Because if you have two variables, it's actually really messy. You still have like a Taylor series. You have two variables and partial derivatives in it. So if you see this truncation error, what's one way that you can make that truncation error small, even though you cut off Euler kind of early? Yeah, you can do a smaller h. You could use a smaller h, but this becomes a problem because if you keep taking, I actually tried this, I remember in one of my numerical classes, there are these differential equations that are called stiff. They just change direction really fast and they have sharp movements up and down, and your code just blows up. It won't work because that you're dividing by, your derivative is just too steep. So your h is going to, when you take the discrimination of the derivative, it's going to freak out, basically. That slope is going to be almost like an infinity slope as it just jumps up really high. And so they taught us a method, backward Euler. and it used matrices, and you had to like program stuff, and like, I'm not gonna do that. I don't want to do that. So I made my H really small. And it freaked. The program freaked because the smaller that the H is, the more cumulative round-off error that you're going to have. I call it propagation of error. So when you integrate something, back in the day when you first learned about integrals, Riemann sums, you're just adding up small pieces. That's really when you just chop up something by h and numerically integrate it. That's what you're doing. You're going back to Riemann sums and the idea of summing something up. So if you have this round-off error each time your loop goes, you're actually cumulatively adding it over and over and over again as you're summing them up. And so the problem is really that even though your h is small, you're adding up error again and again, and that round-off error starts to add up. So this idea of just making h extremely small, like 0.000001, is actually a pretty bad idea, which I found out the hard way. Because technically, then you could just do Euler's method, and you don't need to teach any other methods, and everybody can choose their h really small. It just doesn't work. So this section of the book talks about Rahikata and talks about the total error. It's going to be a sum to get both. I don't want to say too much more about this because I just really feel like I don't want to make this a numerical analysis class. This section that is on the pacing schedule that Colonel Hartley covered, they do talk a lot about round up, like balancing. It becomes an optimization problem, an OR problem. And if you go look in the book, they actually have a graph where there's an optimal point to set your H so that you minimize this sum. So that's the goal. The goal is to minimize sum with small choice of H. Have you guys taken optimization classes yet? No? Okay, you probably will because you get this list of electives and you say, I want to do sabermetrics, I want to do this, and I have to do, I'm kidding. I want to take real analysis and I have to take optimization. Yeah, it's one of those like dirty applied math classes where you have to actually do lots of computation and stuff, but it's good class. Good class. Now, there's nothing wrong with it. But in an OR class, you'll talk about minimizing. Oh yeah, wait, you guys had Lagrange in calc class. So Lagrange is like that. You're trying to take a function and optimize it over a feasible set. So you have a feasible set, you want to optimize this, you want to find the H that does that optimization for you. However, in most of the time, H equals 0.01 for most differential equations works. The only examples I've ever had that it hasn't worked on is those that were given to me in numerical analysis class where that equation was definitely stiff. If you're going into more engineering types of field, you'll have that. That made me decide I'm not going to go do that. I don't want to do that. I don't want to program a whole bunch of stuff like that. So, too messy. We'll probably look at one. Just one messy one so you can see it. All right, so now on your in-class assignment, I actually have you, now that you have Sarah's code, I would just get up for code to Python and just run it, like try it out, put it in there. You're in here, got time, let's do it. So your in-class assignment has